So number 3, we'll reread this. It says a cylindrical tank has a radius of 3 meters and a depth of 10 meters. Okay, we can put those in. So the radius is 3, so that we can put in there. And it has a depth of 10, so that's another thing of saying kind of like the height of it is 10. And it is being filled with water at a rate of 5 meters cubed per minute. So imagine like you have some kind of a tank and you put a hose in it and that it's filling with water, right? You can kind of all hopefully envision that. So it starts with no water in it, and then slowly but surely, okay, it's going to start to fill up with water until it reaches probably the top, and then you'll stop it or whatever. All right, so we have that going on, that it's just slowly starting to increase. So they also say that the rate of change of this happening is 5 meters cubed per minute. Right? And we want to know how fast is the surface level of the water rising. So as you go in and you fill in the water, we want to know, well, how fast is this rising, right? So how fast is the height of the water, if you will, getting bigger and bigger? Is it rising? So let's go in and we'll be consistent with, let's figure out what we want. Let's figure out what we know, and then work from there. So usually what you want is what they're asking, right? It says, how fast is the surface level of the water rising? So you have a couple ways that you can say this, but I'd say something like, okay, how fast is the height of the water changing with respect to time? Right, so I'll use the variable h to kind of think of height of the water as it grows. So dh dt, that's what we want to know. They did tell us that it is being filled with water at a rate of 5 meters cubed per minute. So this is saying, okay, well, the volume, that the rate at which the volume of the water is being pumped in is positive 5 meters cubed per minute. I think that's supposed to be minutes, that m. Okay. What else do they tell us? They tell us that your radius is 3 and that your depth is 10. So now it's kind of important. Is there anything that is not changing in this problem? The cylinder, which, yeah, you're right, the cylinder is always going to be the constant, the same shape, but within the cylinder, the radius is never changing, right? It's always going to have the same radius. The height changes as the water fills, but within that body of water that's taking on a cylindrical shape, the radius is never changing. So R is always going to be equal to 3 meters, no matter what instant you're filling the water in, right? At the beginning or at the end, the radius is always 3 meters. So we have to relate somehow our height to our volume. And this is a formula that I wouldn't expect you guys to remember or know. I would give it to you. But because we're working with rate of change of volume, that tells us or gives us a hint that we're working with volume. And volume of a cylindrical tank or a cylindrical prism is pi r squared. So the area of the base times the height. Okay, and now that we kind of know what we're working with, we can say, okay, well, let's let V, R, and H, and I guess technically T represent. I'm not going to write it all in, but on a test, just make sure you're kind of doing that, right? It's kind of self-explanatory, but be consistent on a test so that you actually go through and do it. Okay, so now I can go through, and because the radius is never changing, I can actually put that in right away, because that's not going to affect my derivative. It's still going to be there. It's always going to be 3. So I can go ahead and say, okay, well, this is pi times 3 squared times h, or this is equivalent to 9 pi times h. Okay. Now I have nothing left to kind of do, and I can take my derivative of both sides with respect to time. So this is going to be the derivative of volume with respect to time is dv dt. And the derivative of 9 pi times h, well, is 9 pi times the derivative of h, which is simply just dh dt. All right, the derivative of h with respect to time. Okay, before I go on and finish this, do we have any questions? Yeah, Leila?
I don't understand why 9 pi is
because it's a constant, right? It's a constant. If you take the derivative of 3x, right, with respect to x, that's just 3, right? You're not doing your product rule, really. Your rules for if you have a constant multiplying by a variable is that your derivative is equal to the constant times the derivative of that, right? Where you have to use your product rule is if I gave you something like, well, 9x times 5x. Like that you could probably multiply together, but technically those are a product of 2 variables and you would have to use, or you can't see that, sorry. Our derivative, somebody want to answer that, is in respect to time.
How do you know
So the easy answer to that is that all of these questions, the derivative is with respect to time. The second answer is because they tell you, or they kind of, it's not really clear, but it's 5 meters cubed per, and that should say minute, right? It should be clear that that's per minute. So that's like, oh, it's per amount of time. That's what it's going to be. And whatever your rate of change of one of your variables is, your other one has to be with respect to the same variable. We're never going to have a derivative or two derivatives with respect to different things, right? They're always going to be with respect to the same thing. Grace? Because we're doing our chain rule, right? It's that the derivative of h is kind of like, if you took the derivative of y, it would be y prime. But our derivative of h is like h prime. However, we don't write h prime, we write dh dt. It's the derivative of h with respect to time. Okay? So it's the rate of change of h with respect to time. Yes? Because if you take the derivative of the left, you have to take the derivative of the right. So we're taking the rate of change of the volume with respect to time, and then we take the derivative of the other side also with respect to time. Okay? Any other questions before I move on? Good. Okay, so we're going to keep going here. So now, do I have anything that I can fill in to my equation that I know? Good, I know the dv dt, right? I know that the rate of change of the volume is 5, so I'll put that in. 5 times 9 pi dh dt. So we get that the rate of change of the height with respect to time is 5 divided by 9 pi. Right? All I did was bring the 9 pi over and it became a division, right? So to isolate for dh dt. Okay, so we have here that therefore, the height of the water is changing with respect, you don't even have to really put with respect to time, it's going to be kind of obvious when you put with your units, is changing at a rate of 5 over 9 pi, and then this is going to be meters per minute, I think is meters, because that was what our time was in the original one, when, and this happens at the instant of r equaling 3 meters. Good question. Yeah, I was just going to say that. Do we need to put, is it really relevant that the radius is 3 meters? Yeah, exactly. It doesn't, you're right. It doesn't actually matter because the rate of change of the water is constantly going to be 5 over 9 pi. That's a good point. Thank you. So you don't really need to put it in there. Yes, Layla? No, because it's height, right? So we're measuring height, which is a linear measurement, right? So that's going to be just meters, not meters squared or meters cubed, just meters.
So if it wasn't like a perfect cylinder, radius, like
Good, we're going to do that next. Are you excited?
Oh, yes.
Yeah, that's the next one. So we're going to look at one where it's a cone. Exactly. Okay. So before we do that, I'm going to do 2 more questions. I think that's kind of more than I can ask for from you guys. So I'll do 2 more, and then we'll do a couple minutes of homework time. I don't know if that'll leave you with too much time, but a couple minutes. So we'll do 4 and 5. We'll see if how fast we can get through this. So you have a 5-meter ladder leaning against a wall, which begins to slide. If the top of the ladder slides down the wall at a rate of 60 centimeters per second, how fast is the foot of the ladder moving when it is 3 meters from the base of the wall? And you'll notice that, like, my other class raised this point. They're like, Miss, how are we supposed to know how to do this? I don't expect you to know how to do these questions yet. And they all kind of say, well, there's no way that I would know how to do this. No, but we're going to practice similar types of questions so that hopefully you recognize, oh, there's a ladder question. I've done this before. Or there's a cylinder question. I've done that one before. Right? They're not going to vary drastically. They're all going to be roughly kind of ones that you've seen before. So kind of bear with me as we go through it. Again, so step 1 that I have to do is I have to draw it. Right? So I'm going to draw my wall and my floor. Imagine it's that. And then you have a ladder that's leaning up against the wall like this. So that's our 5-meter ladder. Okay, and then what's happening as kind of gravity takes over and the friction is not holding it up anymore is that we have that this is going to start to slide down. Yep.
Is there someone on the ladder?
No, that would be bad. No one on the ladder. Okay.
I would be making sure.
Oh, what kind of really depressing math questions you've been doing, but Yuri? I don't know who Yuri is. Okay. So our ladder is sliding down, and as that the top of it goes down. This, hopefully you can imagine, is starting to get pushed outward, right? So it has that relationship that as the top goes down, this goes out. Okay. So this is, it's sliding down. So what we have, and actually, you know what, before we even do that, we have to come up with some variable kind of system, right? We need to know the system of what we're labeling what. So just kind of because it's a little bit out of, guys, can we listen, please? What we're used to. I'm going to make the vertical height y, and I'm going to make the horizontal distance x. Right? I'm just doing that because it's kind of consistent with our Cartesian plane. So the vertical height, I'll make that y. The horizontal height, I'll make that, or the horizontal distance, I'll make that x. So now we can go in that we say, well, I know that the top of this ladder is coming down at a rate of 60 centimeters per second. Right? They're saying that it's sliding down at a rate. So that means that dy with respect to time, so the rate of change of y with respect to time, and this is where I'm going to say, because it's sliding down, I'm going to put that as negative 60, right? Because it's going downward. Right? So being still consistent kind of with our Cartesian plane with where moving down is negative. So we have that. We have that dy dt is negative 60. The other piece of information that we have is that this is happening, or we want to know, when this is 3 meters from the base of the wall. So we also have that we're looking at this specifically when x is 3 meters, right? So when you're 3 meters from the base of the wall. So that's along the ground. And in the question, they tell us, how fast is the foot of the ladder moving? So we want to know, well, what's the rate of change of x with respect to time? Right? So how fast is this moving? And actually, we can go and put this in green. Because in the question, they say, how fast is the foot of the ladder moving when it is 3 meters from the base of the wall? So specifically, when this piece of your ladder is a distance of 3 meters. We don't know where it started. Let's say maybe it started at 1, or maybe it started almost really, really close, and then it started to slide down. And they want to know, okay, at the moment, at the instant, when it is 3 meters away from the wall, what's our rate of change? Okay?
What does dy
over dt represents how fast this is sliding down. So how fast is the top of the ladder sliding down along the wall? Along the wall.
I know dt is time.
Yeah.
What does
So y is this measurement. So we're thinking, how fast is this changing? How fast is the y changing? And this is how fast is x changing. It's good? Okay. Now, this is where this gets a little bit tricky, is now we have to come up with a relationship between x and y. Right? And it's not necessarily very obvious, but hopefully it will be once we've done these questions a couple times, is that you can maybe see that x, y, and the ladder make a right angle triangle. Yeah, so we're going to use Pythagoras, exactly. We're going to say, okay, well, x squared plus y squared equals 5 squared. All right, and that's going to be the case no matter how my ladder is leaning against the wall. Right, it's always going to create some kind of right angle triangle. X and y change, but they still create that right angle triangle. And here we'll say let x and y represent, and we'll just say represent the dimensions in the diagram. Okay, so you have your relationship, and again, wouldn't have expected you to figure that out right off the bat, but these questions will repeat. So now we can just rewrite this as x squared plus y squared equals 25. Okay, so now I have to take the derivative of both sides, which means I'm taking the derivative of every single term, but with respect to time. Okay, so the derivative of x squared is 2x times the derivative of the inside function, which is dx dt. Right? It's the derivative of x with respect to time. Okay, now the same thing for y squared. We're using implicit differentiation, really, kind of y squared is 2y times the derivative of y, which is dy dt. And what is the derivative of 25? 0. Good, so we'll put that in. So the fact that the ladder was 5 meters doesn't matter right away. It will, but for now it doesn't really seem to matter. Okay, so we should, in theory, be left with only one variable. We only want to know what dx dt is. So we should be able to fill in all of these things. Do we know what x is? Good. Do we know what y is? Not yet, right? Not yet. So we need to solve for y.
Well, if we know what x is.
Good. We can figure it out.
I think.
Yeah, exactly. We can figure it out, but we need to solve for y. You're right. So at the instant when x is equal to 3, we're going to use that relationship that, okay, well, 3 squared plus y squared equals 5 squared. And you'll see pretty quickly, okay, that's just a Pythagorean triple, and y has to equal to 4. All right, so it's 5 squared minus 3 squared, 25 minus 9, you're left with 16, and then square root it. It can only be positive, so we leave it as positive 4. Okay, so now we do know y. Good. Do we know what dy dt is? Negative 60. Perfect. Okay. Now I'm just realizing this, and I didn't realize it sooner. Let's just be careful. I'm realizing that it's a rate of change of 60 centimeters per second, but it was 3 meters from the wall. So before we go on and put in negative 60, let's just remind ourselves that this is 60 meters, or sorry, 60 centimeters per second. And then that's equivalent to negative 0.6 meters per second, right? We want them in the same units. Okay, so now we have y is 4 meters, x is 3 meters. Our rate of change for y is negative 0.6 meters, right? We just want them all in the same units. Okay, so now fill in everything. So 2 times x, so 2 times 3. dx dt is what we're looking for, so we leave it as is. Plus 2 times y, we did that work to figure out that y was 4. And dy dt we figured out is negative 0.6, and that equals to 0. Okay, so now a little bit of work to figure out what's dx dt. So we have 6 times dx dt, which equals to 2 times 4 times negative 0.6 is 8 times negative 0.6, which is 8 times 6 is 48, 4.8. And then last but not least, we have to isolate for dx dt. So you'll just, at the very end, divide both sides by 6 and get that the rate of change of x, of that dimension, with respect to time is 4.8 divided by 6, which is going to be equal to 0.8. I don't think so. Okay. And then, so this is our units for this are meters per second, right? Because we scaled everything, or we rewrote everything in terms of meters per second. I'm not going to write it out, but just you include your therefore statement.